Morning, everyone. We're going to start this hard start at around 10:03. Just let everyone kind of roll in. There's a bunch of people signed up, so we'll just wait on them for a little bit, and then we'll start around 10:03. All right, I think we're good here. Uh, Morning, everyone. I'm Mike Pillock with Odell Associates, or Odell HVAC, I guess now. Um, Happy to have you all here. With me is Peter Stumpo and Johnny Graham with Big Ass Fans. They'll be helping us along with the sustainable HVAC design using air movement, essentially using thermal comfort in a D-strat strategy. Um, just a reminder, this presentation is available for PDH credits, so you can reach out to us to get that. Is it a link, Johnny, or a certificate that is received? So reach out to your local Odell rep, and we can get that for you. And further ado, I'll leave it with the Big Ass Fans, gentlemen.
Awesome. Thank you, Mike. Welcome, everyone. I'll just get the screen shared here. Okay. So if anyone can't see that, let me know. Thanks for the intro, Mike, and thanks for having us. And for everyone that joined, I'm Johnny Graham, National Sales Manager at Big Ass Fans Canada. I've been with Big Ass Fans about 10 years. We have Pete Stumpo on the line as well, one of our technical salespeople. So we'll try and answer questions at the end. If you have any, take notes throughout, and we'll jump to that at the end. Okay, so again, the topic today is sustainable HVAC design. So we'll get into what that ultimately means. A few themes throughout you're going to see today. Thermal comfort will be at the core of all of this. So we'll touch on how we define that, how we control for it. We'll get into what the fans actually do with regards to cooling effects, perceived cooling, and ultimately destratification during the winter months. And then we'll wrap with some application examples and some additional benefits that you might not think of with ceiling fans. Okay, thermal comfort, let's start there. The definition, the wordy definition from ASHRAE, is that condition of mind which expresses satisfaction with the thermal environment. The key word there at the end being subjective. So a less wordy definition of that is really that this is a matter of perspective. We're talking about your thermal comfort is likely the lack of noticing discomfort, right? Most people are not actively perceiving I'm comfortable. They notice when I'm hot, I'm cold. So that's what we're trying to navigate and constantly balance. At the end of the day, it's the ability to focus on the work at hand. So what we want to do is design spaces where people feel comfortable to perform, to be at their most productive, and to be comfortable in the space. Okay. So technically speaking, 6 factors go into this at any given point. We're going to talk a lot about airspeed today, but the other 5 factors are equally paramount to what's happening. So air temperature, of course, just the radiant temperature that combines with that. Those 2 factors are going to perceive or make the person perceive ultimately what the temperature is in that space. Humidity is going to affect that as well. Okay, clothing and insulation, that would be more of a personal factor. Same with metabolic rate. The 4 environmental factors are really what we influence on the design side. And then what we're talking about today is how we supplement airflow to ultimately bring up or down someone's thermal comfort depending on the ambient temperature in the space. So starting with clothing insulation, again, this is a personal factor. It's going to depend on the type of environment, but ultimately what ASHRAE has done is created numerical values that you can assign to different layers of clothing. So sounds weird, but we definitely want to know what people are wearing in spaces so that we can design our solutions accordingly and adjust our HVAC systems accordingly. So just as an example, what you're seeing there, a total clo value of 0.41 would be something indicative of like an office space. If you're adding a jacket, now we're adding 0.6 and we're getting more and more thermal insulation. So insulation on your body is inversely proportional to heat loss. So effectively what that means is the more layers you're adding, the more heat you're trapping. So it's harder to regulate your body's temperature. The image of the individual working out, obviously lower clothing level, you're going to hopefully have some air speeds to wick away moisture and constantly break down that barrier that's causing heat to be trapped. So clo level is something we want to make sure we're monitoring and we're planning for when we design these spaces. Another factor, again, this is personal, but metabolic rate. So metabolic rate effectively is proportional to heat generation. The more energy you're expending, the more heat you're generating. So just a few examples on the right, me right now giving you this presentation, I should be, 1, maybe 2. Had I gone for a run before this, which I definitely did not, would be 8 to 10, right? So metabolic rate being at 8 to 10 would generate a lot more heat, and my body would struggle to try and wick away that heat gain and regulate my temperature. So metabolic rate is something we want to keep in mind because how aggressive we are with cooling in a gym versus an office is definitely going to come into play at the onset of the project. So we want to keep this in mind. Air velocity. So this is really where you can use fans to supplement a lot of the cooling that's needed in a given environment. What we're doing with air velocity is wicking away moisture, like I alluded to. We are not changing the temperature of the space. So this common misconception is, fans make a space cooler. By definition, they actually don't. They make a space feel cooler, which is a perceived evaporative effect on our skin. Okay, so it sounds gross, but all of us, whether we're, MET rate of 1 or MET rate of 10, we have a sweat barrier on our skin. When we break that down with airflow, we actually increase the heat loss from our bodies, which make us feel cooler. So the best example I give is, if you're driving down the highway, you don't have your AC on, it's 30 degrees out, it feels like it's 30 or 35 in your car. As soon as you roll down the windows, it's still 30 degrees out, but you might feel like it's 20 because you're getting that rush of air across your skin. So that's what we're doing with air velocity. It's tailored to the environment so that it's not disruptive, but it's ultimately providing that supplemental cooling. So we'll get more into that later. And how we quantify this, it's not guesswork. This has been mapped out by others, ASHRAE, University of Cal Berkeley, Thermal Comfort Tool. So what we have here is just an example of what would likely be an office environment based on the assumptions in the bottom right. And you can see as we elevate the airspeed in feet per minute along the bottom axis, the cooling effect in Fahrenheit is rising. So, just as an example, in an office, you might shoot for 120 feet per minute because, we've tested at our R&D lab that papers start to flutter after that point. So you don't want to disrupt the space, but you want to add a little bit of supplemental cooling and airflow to create that comfort that we need. So at 120 feet per minute on this chart, we're talking about, 6, maybe up to 7 degrees of a perceived cooling effect, which is pronounced, right? So you can really beef up your cooling system by just adding some airflow to a given environment. So that's what we're doing. And why are we doing this? So we want to make sure that people are happy. Couple terms you're going to learn today. So PMV, predicted mean vote, which would be that somewhat oversimplified sliding scale along the bottom. This is actually an ASHRAE tool. So the PMV is the sensation of thermal comfort. So if I were to survey everyone on this call, what is your thermal comfort level on this sliding scale of warm to hot, cold to warm? We want to make sure that you're somewhere around neutral. So 0 would be ideal. If you are negative 0.5, so really just starting to err on the side of cool, up to positive 0.5, you're just starting to be a little bit warm, you're still within that neutral zone. So you can see by that correlating chart or that line, if we are around that neutral scale, we should have most people in the space satisfied. So on the y-axis, you can see PPD. PPD is another ASHRAE term, so predicted percent of dissatisfaction. If we are relatively neutral with the sensation, 90% plus should be satisfied. And that makes us happy, that makes ASHRAE happy, and that should make most of the people in the space happy. We all know this from working in different environments. You're never going to keep everyone thermally comfortable, but you want to please the masses is what we're getting at. So what does this actually look like when you apply it? The thermal comfort tool is something that is published online. So you can go on today, CBE, which is California Berkeley Labs. You can use their thermal comfort tool. It's a free resource. And those 6 factors I just talked about are actually inputs along the left side that you can see there. So in this environment, set point is roughly 73 degrees. We have negligible airspeed. So 19 feet per minute is not perceivable. Anything under 40, you do not perceive as a human being. So that's basically any ambient space with no fans. Relative humidity 50%, MET rate 1.2, so it's probably an office environment, and the clothing level would be indicative of that as well. So what do we see on the right? So we see a chart with a blue streak. That blue streak is what we call the comfort zone. So we want to be plotted somewhere on that comfort zone to be compliant with ASHRAE standard 55. So if you look at the top, those terms I called out earlier, PMV, PPD are listed. So based on these inputs, the PMV is negative 0.35, which means they are actually within that neutral range. Again, erring on the side of cool, but they're happy. And the PPD as a result is 8%. So we expect 92% of the people in this environment to be happy. So this is a good thing. We're going to circle back to this later, and we're going to do a couple experiments with it, how we can push that operative temperature up and ultimately raise our set point. But just footnote this for now, because we're going to come back to it. A few other things I want to let you know is, along with ASHRAE, some of the standards that we help kind of contribute to with air movement, there are other bodies like LEED or even Green Globes, not listed here, where we can actually help you get some credits for what your building project requires. So there's some prerequisite credits. There's some additional points that you can earn just based on adding fans from a sustainability side of things. So if you have projects, talk to your Odell rep, ask us. We have some experience with this, and we can share what credits you can possibly hit on by incorporating a fan solution in your building. So just keep that in mind. Some glamour shots, Mike's house there on the left. Fans and cooling effects. So we're going to get into what we actually use these products for. Again, we touched on how we cool people. It's a perceived effect, but what does this actually look like in application? So whenever we design a solution for cooling, a couple things we really want to know. Number one, where are the people? Because, in this example, you're seeing a CFD model with racking towards the planned north side of that building. We likely wouldn't put fans in those racking aisles unless we know that there's people constantly in that space, which that's usually a transitional space. So we're probably putting cooling where you're seeing these CNC machines or some kind of workstations. So like I said off the hop, you're not changing the temperature in the space. You're just delivering air speeds for the purpose of evaporative cooling. So you really need to focus the fans where the people are, where the activity is, to make sure you're maximizing that effect. Okay, so in a space like this, it's probably a factory, likely no mechanical cooling. So we're really just relying on airflow and circulation to keep people comfortable. So what we're thinking about in this environment is getting the highest practical airspeed to keep people as comfortable as possible. Like I alluded to, practical may be limited by things like paper on desks. So if this was a classroom, I probably wouldn't be so aggressive with the fan placement and the fan speed. But being a factory, you don't have mechanical cooling. You really need to beef up the airspeed to compensate for what is likely a very hot, uncomfortable environment. So designing for cooling, focus on the people. What I will say as well is always push for a CFD, so a computational fluid dynamics model, which is an example of what you're seeing on the screen. This is something we do for free, but I think it's important, whomever you're working with, to get that verification of the air speeds, because you cannot see airflow. You can sort of predict it, but if you have something that can model it, that's really what's going to tell you, does this work or not? So this is how we design for cooling. And when we take, a traditional environment, like I showed you on that ASHRAE tool, now we're looking at Celsius, but typical set point, maybe it's 22, maybe it's 23, could be a little bit higher depending on the environment. Again, relative humidity is probably around 50%. So in this example, we're looking at these 6 variables again. Airspeed's 30 feet per minute, which, as I mentioned, anything under 40 you don't feel. So this would be like your conventional design building, no fans, ductwork, diffusers, you're dumping in cold air, you're trying to keep it comfortable. Metabolic rate and clothing level, again, is indicative of an office. So we're going to have some fun with this. Again, if you plot this on that chart, you can see that they are comfortable. The PMV is 0.47, negative 0.47, and 90% of people are happy. So this technically complies, but pay attention to that set point of 23.8, that ambient temperature. Because now what we can do with fans is raise that set point a few degrees. Every degree you raise is usually about 3 to 6% electricity savings. And that's from the Department of Energy. So if you can do that, you are doing your building a service. You are helping the owner of that building save some money, and you're also helping the environment. So we're pushing that envelope a little bit. We're going to raise that set point. But what we're adding here is a modest air speed of 145 feet per minute. So this would be comfortable for an office. This is not going to be disruptive, but it's going to get you a little bit of a cooling effect to supplement that ultimate cooling load that we're sacrificing by raising the set point. So what does this look like when we plot it? Again, people are still comfortable. PMV stayed relatively flat, negative 0.48, and we still have 90% of people satisfied in the space. So we've raised the set point almost 3 degrees. We're saving, again, between 3 to 6% per degree, and the sensation is neutral. So we've added fans that draw very little power, and we've reduced the usage of high intensity cooling mechanisms like an air conditioning unit. Let's push this a little bit further. So I've raised it to 29 degrees Celsius now, which in most office environments, people would be losing their marbles. I can tell you that because we work in one. And if someone sees the thermostat at 29, they would be not thrilled with that. However, if you actually just look at the math, they would feel the same sensation as if it was 23 with no airflow. So this just shows you how far you can push it. We work with a lot of customers where their goal is carbon offset, or they're just trying to save money on their AC, which is getting costlier and costlier. And we've pushed this pretty far without any jeopardization to the actual staff or the occupants in the building. So again, we can achieve thermal comfort in a multitude of ways. Fans are a low cost and relatively low energy intensive way to do it. So this is just an example of that. So let's look at just some real applications where what this would look like, how we would go about it. Typical school gym would have a main trunk of ductwork, usually some redundant legs to try and push that conditioned air throughout the building. So this was a study we did near our head office in Lexington. So set point 22, you want to go a little bit cooler in a gym because of the high MET rates. And, it feels like 22, obviously, because that's what the set point is. Materials and installation costs, just note that. Obviously, sheet metal is not cheap. There's an install cost to that. So we'll look at how that compares when we drop some of these redundancies. So if we were to add fans in an environment like this, oftentimes what the engineer will do is cut down on those additional legs of ductwork and simply dump the air in the space and use the fans to mix. So oftentimes with the fans, you're getting 2, 3, 10 air turnovers per hour. So you really don't need all of these legs of ductwork trying to disperse conditioned air. That fan is going to push it down to where it needs to be and constantly recycle it through the space. So immediately we can see the materials and install costs actually went down, even keeping in mind we're installing fans. The set point we've raised, so we've gone from 72 or 22 degrees Celsius to 25 degrees Celsius. So we've raised it 3 degrees. We're using that supplemental cooling from the fan. We're saving some electricity costs, and let's see how that all shakes out. So again, materials and install costs dropped, modestly, but again, it's helpful. AC consumption dropped significantly. Again, 3 degrees in this case actually translated to 38% off of their electricity bill in the summer. Annual utilities costs for destratification purposes dropped 17%. So we're going to touch on destratification, but effectively we're pushing the heat down to where it needs to be. So their heating system was not working as hard. So they saved 17% on their annual gas bills. So when you bundle all that together, it's pretty attractive. Again, it's a more efficient space. It's usually less upfront, and then you have the long-term benefits of energy savings. And just a quick visual. I mean, obviously, this is conventional, what you would see, ductwork throughout. Architects love when we can rip that out and put something a little sleeker. We can even blend these types of products into the ceiling, custom color, whatever is needed. And it's a little bit more controllable too. Again, you have fans where you need them, speed them up and down as needed. All right, so we're going to watch a quick video because on the topic of gyms, we often get the question from engineers, is this safe? Does it need a cage? It does not need a cage. So this is not a very scientific test. I'm going to just footnote that, but enjoy nonetheless. Yeah, these are not professionals. We'll just be clear with that. Okay, I think we get the idea. And again, we have an R&D lab. This is not it, where we do test things like this. But we want to show this because oftentimes people are concerned, is the fan going to be damaged by a ball in a gymnasium? It is absolutely not. These are designed to take a hit in that capacity, stay on the ceiling, number of redundancies with the safety features to keep these types of products on the ceiling and safe and operating for years to come. So keep that in mind. And we have one more video, which I think really highlights one of the things that is a common concern in manufacturing or more industrial environments where you have a forklift that is raised and ultimately comes into contact with the fan. Not an ideal situation, but there are designs implemented to keep these airfoils on the fan. And one of them is what's called an airfoil restraint system. So it's always good to ask for this because this is something that, again, it's a strap. If the actual system fails and the redundancies fail on the mechanical side of that airfoil, a strap will hold that airfoil on. So we'll show you what that looks like.
At that R&D facility of our airfoil restraint system on our new Powerfoil D model fan. As you'll see, the fan is impacted, shuts off immediately, and stays intact, keeping you safe. See for yourself. At Big Ass Fans, safety comes first and second and third.
So what you saw there effectively was a couple things in motion. So number one, there's an accelerometer built into the fan. So as soon as it senses a difference in rotational speed versus the set point on the VFD, it's going to trigger that fan to shut off. So it's not trying to constantly spin once an impact happens. The other thing that's happening is there's 3 redundancies effectively that you just saw in action. One of them was hard to see, but ultimately there's hub retainers that are holding those airfoils on in addition to the spars. And if that were to fail, within that entire airfoil is a safety strap similar to a seatbelt that connects at the end of the winglet all the way back to the hub. So it's not rigid. If something hit it with enough impact to snap all of the other redundancies, that airfoil actually would stay on the ceiling, the fan would stop, and it would be dangling from a strap and not on the floor where your people are. So again, just a quick pit stop on safety. We want to touch on that because these products are large. We want to make sure that you're buying something that's safe and effective in these environments. Okay, so jumping over to, we talked about gymnasium space. Let's think about the same type of application, but in a slightly different environment. So we're still trying to reduce these ductworks, legs of ductwork, I should say, and we're ultimately using fans to mix the air. So this is a conventional office space where you would have a drop ceiling, these square diffusers throughout. Again, those branches of ductwork that we often see. Set point a little bit higher, 23 degrees, and just note the materials and install costs. Now, when we add a fan or fans to this environment, you can see we're sticking to one simple ductwork down the middle with sidewall diffusers that are going to blow into the space and the fans are going to mix. Okay, so we've raised the set point again a couple degrees, saving that electricity, keeping people comfortable. Now you have individual workstations effectively with their own comfort zone because they can adjust the fan as needed. And again, we're saving on the materials cost pretty substantially here. So when we summarize, materials and install costs went down significantly. We know T-bar ceilings are not cheap. The install cost associated is expensive as well. So we're reducing that. We're opening the building up and we're using fans for D-strat and mixing. So AC consumption dropped by 24%. and utilities costs 10%. So again, still some savings on the gas side in addition to the summer electricity costs. And just a visual on what that would look like. This is a lot of offices today. Many architects want to open that up. A little bit more fresh air, natural light, higher ceilings. People like these types of environments. So if you can use the fans to mix that air, you do not need that drop ceiling, right? The whole purpose for T-bar ceilings is to keep heat where it needs to be because it's constantly rising. If you have fans, you effectively have eliminated the need for that ceiling. All right, so just to summarize, coolant effects and savings and what we just touched on. So we really want to offset thermostats in spaces, especially on the cooling side. If you can raise your thermostat, like I said, 3 to 6% savings per degree can be had. Ultimately, with this too, you're running your system less. So one of the savings that you don't often think about is just the maintenance costs and filters and fixing rooftop units because you're running them more than you need to. So you're running your equipment less. There is reduced CapEx on new builds. So we can talk about, kind of on the front end of jobs, if we can reduce tonnage or legs of ductwork, that's only going to help. And then we are also reducing OpEx. So constantly, you're running these buildings, you're using less electricity, you're using less gas. Anytime you can do that, you're saving money and you're also extending the life of your equipment. So the last piece, which we'll touch on a little bit later, is productivity. So productivity is, again, proportional to thermal comfort. So there's a correlation there, and we're going to touch on how that looks. There's been some peer-reviewed studies that have showed as soon as you get over 21, 22 degrees in a space, productivity starts to dip. So there are things we can do to keep that productivity high. Okay, so let's look at specifically destratification and what that means and how we use fans to achieve it. So some definitions to start with. Stratification effectively in this context is the natural tendency for heat to rise. So cold air is going to settle, the warm air, less dense air is going to rise. And this is a constant losing battle for anyone trying to design a space or anyone trying to keep a space comfortable. So just the image on the top right is, again, oversimplifying, but definitely showing you what a lot of buildings do look like if you were to look at it with a thermal image gun. Typical delta from floor to ceiling in a building that's 30 feet might be 10, 12, 15 degrees. So if you think about all of that wasted heat energy that's just at your roof deck, having a fan to constantly recirculate that air, you can shrink that delta to about a degree. So HVLS fans, high volume, low speed fans, are not only great at providing cooling, based on the nature and the size of those units, they are going to turn that air over constantly in the building and keep that air mixed. So ceiling heights above 15 feet, you're going to have some degree of stratification that is making it challenging to keep the building comfortable. For everyone, you can know that about a degree per foot of height on the Fahrenheit side. For Celsius, it's about half a degree to a degree per meter of height. So that's effectively the degree of stratification you're going to see. Insulation is certainly a factor we have to look at as well. Type of heating equipment is going to play into that. But just generally speaking, that's what you're looking at. So what we want to do, again, is just mix that warm air down, have your heating kick on less. And if you note where the thermostat is in this image, as we know, it's usually 5 or 6 feet off the ground max. So all of your heat's at your roof deck and your thermostat's trying to manage the set point. It's constantly going to cycle your heaters, even though it's a losing battle, right? And that's what we do not want. So typical savings, I see up to about 30% on gas savings in most buildings with tall ceilings, which can be substantial on the financial side, but also from a carbon emission side. Many people are looking at carbon offset. This is an easy, low-hanging fruit for us to attack. So we talked about designing for cooling, right? We're putting fans where people are. Designing for destrat is a little bit different. You definitely want to know where people are, but you want to make sure that you are addressing the entire building wherever you're heating that building. So it's more of a broader approach. You want to make sure you're mixing the entire air volume as opposed to creating high elevated air speeds directed at people. So with destratification, you're often going to run the fan slower. So in the winter months, you definitely don't want to breeze. All of these types of products would have a variable speed drive, if not sensors or temperature sensors in the control to adjust speed accordingly. So they're very intuitive and intelligent when it comes to not creating adverse effects in the winter, but mixing the air and achieving what you need, which is that temperature homogenization. Okay, so you can space fans a little bit further for destrat when we're designing these solutions. It's not as aggressive. We don't need full coverage of every square inch of that building for cooling or where the people are. We just need to get enough air turnovers per hour, which is what we measure to make sure that you're getting enough for destratification. So if your building was 1 million cubic feet of air volume, we want to make sure that we're getting at least 2 air turnovers per hour. So about 2 million cubic feet cycling through the fans per hour to get at least the minimum threshold of destratification that we want. We also use that CFD modeling tool that you saw to make sure we're quantifying it, we're getting the right patterns of airflow, and we're getting enough turnovers in that space. I will call out here, do not reverse the fans. It is a much less efficient way to bring that warm air down. You're also blasting heat at your ceiling deck, which is the usual thinnest point of insulation. So what's going to happen there is you're just going to speed up the convective heat loss through your roof deck, and it's actually a negative impact to the building. So don't reverse the fans. That's an old adage that was based on, fans that had 2 speeds in the 1980s, where basically there was no comfortable speed to run it in the forward direction in the winter, so they had to reverse it. These big fans, they're like an airfoil wing or a plane wing. Don't reverse it. They don't work well in reverse. But if you run them slow in the forward direction, you're going to achieve what you ultimately need to do. And there's just some images around that. So you can see on the bottom right, again, just speeding up that convective heat loss is probably the biggest challenge with running it in reverse. And the other thing is just the obvious and kind of the common sense aspect, where that is the longest path to get that heat to the ground. So the conventional wisdom is like you run it in reverse, you push the heat across the ceiling, down the walls to the ground. That sounds amazing in theory, but that really does not happen. You're seeing something like you're seeing in that graphic on the right, and you're not helping with stratification issues. Run it slow, use less power, so you're not running that fan as fast, and you're going to effectively push that heat to the ground where your people are, and like I said off the hop, where your thermostat is, which is almost as important, because that means your heating is not going to turn on as much. Okay. So quick study on the destrat side. We took a hangar project that was, again, near our head office, and we did a study with them. So they had 36-foot ceilings. We ended up installing one 24-foot diameter fan, so massive ceiling fan. And we want to measure the temperature in the space. We want to look at their heater run times and ultimately their gas usage and how we can impact that. So when we installed those temperature sensors, we placed them at strategic heights. So 5 feet being like your thermostat height, 15 about midway up the space, and then 35 feet close to the roof deck. So what you're seeing is about a week's worth of data, temperature data over time, and you can see the floor to ceiling difference is probably about 10 degrees Fahrenheit. So similar to what I mentioned off the hop, every foot of height is going to be some degree of stratification. We're seeing that here. The spikes are effectively your heating system kicking on and off to try and maintain that set point. Okay, so what you're going to see once we turn that fan on within really moments is this. So we are effectively shrinking that delta in temperature again to, like I said, 1 degree or less, and we are homogenizing all of the air in that space relatively quickly. So this means that the heating system is no longer working harder than it needs to, and we are keeping that space comfortable. So if you picture a door opening, like a big hangar door, all of your heat's rushing out, you have to compensate for that. So if you have trapped heat at the ceiling, the fan can help alleviate some of those dips and maintain comfort while you have, heat loss in the building. So just keep that in mind, and what that translates to is some significant gas reductions. So what you're seeing is 2 tests. So kind of the top portion and the bottom portion. We ran this over 2 separate weeks just to make sure that we're doing this accurately and we're getting good data. So the thing to pay attention to here is, the outside air temperature did not really change. The occupant level temperature was neutral because we want to maintain a certain set point. And the gas usage is where we really saw a reduction. So with the fan on in the first test, we saw almost 11,000 cubic feet of gas reduced just for 1 week. On the second test, it was actually a little bit more pronounced, just based on some of the temperature conditions. So this is typical, and we did not have an aggressive set point here. It's a hangar. The CLO level would be high. People are comfortable at a lower temperature, and still we saw a significant gas reduction. So we can extrapolate this. We do lots of warehouse projects where you're seeing 30% reductions in your gas usage. What does that translate to dollar figures? It's a lot, right? So this is something we can do on the industrial side. Again, we summarize this here, just what the net savings were. And this is also keeping in account what does that fan draw as far as power. So we're looking at that fan operation cost as well, which, as you can see, is pretty negligible. So net savings in this case was about, this was US dollars, almost $2,700. We did this a long time ago. On a product like this, that's probably a 3 or 4 year ROI, right? So not only are you improving comfort and reducing carbon, you're actually eventually paying yourself back, which is nice. So on the commercial side, there are applications that call for this as well. So, this was another study we did, similar type of study where we set those temperature sensors throughout, and we're looking at effectively what the stratification effect is and how we can reduce it. So this was a library, tall, common area. We use smaller fans, but ultimately achieve similar results. So in this study, you can see the temperature delta in the blue lines, that's floor to ceiling, so 4 feet up to that highest sensor, which was 18 feet. And then the orange line is just showing you that stratification deviance over time. So as soon as we turn that fan on, like you probably guessed, we shrink that, right? So you're seeing, again, a reduction to about 1 degree delta. People are comfortable, heat is kicking on less, and you have fans that are quietly and effectively mixing the air in that building. So just to summarize, we did reduce the HVAC unit runtime about 16%. We reduced that temperature delta to 1 degree, like I mentioned. And an important point as well is we only added about 1.7 dBA in background noise. So, when you're thinking about sound levels in spaces, especially something like a library, you want to make sure that you're not adding, an excess amount of background noise that's going to negatively impact the space, even though you're positively impacting the space on the thermal comfort side. Sound is cumulative. So if you had, 20 fans that were all relatively loud, you're going to notice that in the space. So it's, that's a problem. That's something we want to make sure we're vetting on the front end of jobs, and you have the right products to fit with these spaces. Okay, so we'll look at one more here, and this was really an extreme example. This was a hangar project, and we see this all the time, but we're talking ceilings of 60 feet plus, and that's where you're really getting into that 30% savings when you can fully effectively reduce the stratification in that building. So hangars are great, low-hanging fruit, minimal insulation, massive doors that open, lots of heat loss, and ultimately lots of challenge for their heating system to keep up with that heat loss. Right. So we'll look at a few examples just on the application side. Again, how we quantify this. So what you're seeing on the screen is our CFD modeling software. We call it Spec Lab. But again, I encourage anyone who's working on a design that involves fans to ask for a CFD. Again, you're going to use this to vet airflow, to measure performance, and ultimately validate what you're saying you're doing. So it eliminates that rule of thumb. It also allows you to account for obstructions. So one thing I often have to remind people is that air does not move through barriers. It seems intuitive, but it's often something we have to address because racking, obstructions, equipment, even people to some degree is going to impact the pattern of airflow in your space. So if you can model that, you can effectively prove or disprove whether or not something's going to work. So use CFD. This is something we have in-house. Talk to Odell if you have questions about that. This is something we can help you with. And then how do we apply this? So just some more local examples, I suppose. Hewitt, their office in Oakville, we worked with Red Studio Architects to design a system that reduced the amount of tonnage and redundant legs of ductwork in their space. So we use 17 commercial fans. You can see them in the image there. They relatively blend with the space. And overall, we were able to reduce their tonnage and ductwork by about 90%. Okay, so coverage as far as the distribution of the air stayed the same, but we reduced the amount of redundancies in their system significantly. They were able to raise their set point as well because they're using the fans in the summer as a little bit of supplemental cooling. And then they also were able to reduce the lighting grid in sizes. So this just helped them have more play at the ceiling, a little bit more flexibility. Aesthetically, it's a nicer space. And, from a mechanical engineering side, it's a little bit more up to speed with what they need for that type of environment. Another good example, Canadian Tire, they use fans for destratification. And like I was alluding to, they actually found that they were saving additionally on things like HVAC filters, maintenance, replacement belts, and it was about $1,000 per year. So something you don't think about, you may be saving a couple $1,000s on the gas side, but they installed 4 of these fans and they were saving about $1,000 a year just on maintenance of their HVAC system because it was running so much less. So really any application, especially as you get into tall ceilings, you're going to find usually a significant ROI and a good fit for products like this. This is an extreme example. I was somewhat alluding to this with the hangar study, But this was for British Airways, and they were seeing about $114,000 in cost savings in the first 4 months. And that's just by reducing the amount of mechanical heating for that space. So significant stratification effect using 5 fans to destratify that building. Their ROI would have been within like months. And that's, it seems crazy, but this is something that we can effectively do pretty consistently, especially as you get into these larger, poorly insulated buildings. And if anyone's been to Punta Cana, you would probably see what looks like a big fan museum down there because they have 30 of these throughout the airport. A little bit different. They're not so much worried about stratification being in Punta Cana. They want cooling. So it's an open air airport. They're actually using these fans to create that elevated airspeed that I showed you off the hop, where it's creating comfort for people that are waiting in, queues or walking through the airport, trying to keep them comfortable while they go on their way. So I think they're now up to about 38 fans throughout that airport to cover most of the actual occupied space. And typically what they're seeing is about a 6-degree cooling effect within that space. So, it's probably 30 degrees in the building. If we can drop it to a perceived temperature of 24, people are going to be a lot more happy as they navigate the queues and work their way out of the airport. So just another example you may not think about. And then this is just the last example here. So it's not necessarily for people. These fans were installed to help maintain the health of the plants in this environment. So there are a lot of nursery projects or greenhouses that require airflow. Again, it's not necessarily for human comfort. It is for things like wicking away moisture or creating leaf flutter for certain plants that need to improve the stem strength. Product loss is a big deal for a lot of these companies. So we see this question come up a lot. Can you help with, crop loss or mold prevention or things like, mites that may form on certain plants? And usually the answer is yes, because you're wicking away moisture and you're also creating the airflow through the plants to create that stem strength to allow them to grow taller and helping to break up stagnant pockets of humidity as well. So something you may not think about, but certainly another application where these large HVLS fans can come into play and have a pretty significant impact. Okay, so we'll wrap up with a few additional benefits that, again, you may not think about, just to continue that theme. I talked about this, but comfort and productivity go hand in hand. So, as you get too cold in a space or too warm in a space, effectively you are losing productivity with whatever task is trying to be performed. So if it's a school environment or it's a factory, this has been measured and studied, and there is a correlation of productivity loss. Can you, get granular with this? Likely not. It's certainly still subjective to some degree, and there's a lot of variables that go into it. But again, these are peer-reviewed studies through the Department of Energy and through Berkeley Labs, for instance, that are vetted, and there is certainly an adverse effect as you get discomfort in a space. So we want to make sure that we're, again, keeping it relatively neutral and keeping productivity high, because there's certainly a cost to that. Another environment that you may not think of is a pool environment. So, why do you need a fan in a pool environment? The biggest thing is actually to dissipate the chemicals. So oftentimes in these aquatic environments, you have harsh chemicals, poor air quality that hovers right above the surface of the pool. What you want to do with a fan is gradually push those off the surface, up the walls to the exhaust points. So you're never going to run the fans too fast. You do not want to speed up the process of evaporation or make people feel cooler than they need to, but get that gradual, imperceivable airflow, which again, as I alluded to, 40 feet per minute or less, just to wick away some of those chemicals in harsh breathing zone areas. So that's what we're doing in these types of environments. Another big piece is condensation. So again, not thinking about people here, thinking about product. We've seen cases where they were losing hundreds of thousands of dollars a year just in corrosion costs. So if you can raise the temperature of things like steel coils or even a concrete slab, you can reduce that temperature delta, which means when the warm air kicks on and hits a cold surface, there's less of that dew point effect happening. So we can raise the temperature of the ground, reduce that condensation effect. And if the condensation does occur, you're using fans to wick away that moisture. So it's evaporating much quicker. This could be a safety issue. We've seen cases where they had forklifts slipping or people slipping, or again, you have those corrosion issues in any kind of steel manufacturing plant. So condensation mitigation is actually a really huge advantage with these types of products. And then lastly, so improved air distribution. So when we think about supplying air to a space, there's usually about an 80% effective rate when you're thinking about the CFM you're providing versus what you're exhausting, and ultimately what you're trying to deliver to the occupied zone. So what we can do with the fan is again, mix that air a little bit more effectively, so that instead of an 80% factor that you're trying to account for, you can actually provide the appropriate amount of CFM, knowing the fan's going to mix all of that down to the occupied zone. So you're not overcompensating on the supply as opposed to what's being exhausted. So again, just on the efficiency side of things, these fans will help mix the air and help improve the existing systems that are already in place. Okay, so we're going to wrap up just to conclude some of the key points we touched on today. But I do want to talk about one thing, and this has, again, been a theme throughout. But when we think about thermal comfort, it's not just people, it's not just the cost savings, but there's also the carbon emissions and the carbon reduction that we're trying to look at. So we did a bit of an experiment with the data in the US. So we've looked at a bigger population and said, what would happen if we effectively were able to reduce the AC usage in the US? So if we look at what the baseline today is, roughly 6% of electricity in the US was for AC. Again, this relatively old study, it's only gotten worse since then. But that's almost $30 billion just spent on AC by consumers in the US. So when we think about the carbon side of that, we're looking at close to 120 million metric tons. Okay, so what we're thinking about is, what if we raise the set point in homes an average of 6 degrees? What you saw today is that that's very possible by just adding elevated air speeds and low energy intensive products like fans. So if you were able to do that, we would ultimately eliminate 35 million metric tons of carbon emissions, and that's per year. So again, something simple as adding fans for supplemental cooling, raising the set point of high energy intensive equipment like air conditioners, you can achieve something like that. And what does that ultimately look like? 35 million metric tons of carbon. Well, it would be the equivalent of parking 7.4 million vehicles for an entire year. It's about the same amount of carbon that would be sequestered by 29 million acres of forests. And if we're talking CFL bulbs, switching to from incandescent to CFL, that's almost 1 billion bulbs that you're swapping. And perhaps most impactful, it would be like shutting down 9 coal-fired power plants for an entire year. Okay, so this is something very simple, the concept we're talking about, but if we're able to shift that dynamic in how we design spaces, we can have really impactful results like what you just saw. So to wrap up, as far as learning objectives from today, we talked about thermal comfort. We know what that is. We've gone through the definitions and how we quantify it. Heat transfer, so we get how heat's flowing through a space and how we're trying to navigate heat loss. And then when we look at fans plus AC, how do we balance that comfort and use ultimately the least amount of electricity possible? And then we touched on the ancillary benefits to wrap up. But again, that's where I'm going to close it today. So I hope that this was informative. If you do have questions, we do have some time now. And again, if you need credits, we're going to get you that information towards the end of the presentation. Turn it back to you, Mike.
No, I appreciate that. Very informative. I've been in that presentation 3 times. I always pick up one more tidbit of information. So 10 more and I'll have it figured out. But no, I'll open the floor to anybody that does have a question here. Feel free. We'll wait here for a minute or so, and if no one has it, we'll go on our merry way. All right. Nothing. It was that informative. So no, we appreciate it, obviously. That was great. So again, reach out to Odell if you do need your PH credits approved, and anything D-Strat, you can also talk to your local Odell rep. So appreciate everyone being here. Put aside an hour of your busy schedule for us, and have a great Thursday.
Thanks, team. Appreciate it, everybody.
Thanks, everybody.
Bye, Pierre.